EDX Mechanics 1, Workenergy and Power 1, Workenergy, Conservation of Energy. We've seen that the gravitational potential energy lost is equal to the kinetic energy gained when an object falls, and these are both equal to the work done by the gravity. This gives us the principle of conservation of mechanical energy. In other words, when the only force doing work on the body is gravity itself, then the final mechanical energy must be the same as the initial mechanical energy. For example, a ball of mass 0.3 kilograms falls a vertical distance of 4 meters from rest. Calculate the initial potential energy, and assuming that air resistance is negligible, calculate the final speed of the ball. So, the initial potential energy, or gravitational potential energy, if we take ground level as being 0 height, then the initial potential energy we can get from mgh is mass 0.3 times gravity 9.8 times height above the ground 4 meters, which gives me 11.76 joules of potential energy. Air resistance can be neglected, so we can say that final mechanical energy must be the same as initial mechanical energy. So the only final mechanical energy we have is kinetic, so that's half mass speed squared. There's no potential energy at the end, and the only initial mechanical energy we have is potential, which we've just found is 11.76. There was no kinetic energy initially, and that gives us the speed of the particle at the end of this journey is 8.85 meters per second. So that's an example of conservation of mechanical energy because air resistance was neglected. So we're going to take things a step further now and start looking at the work energy principle. We've already seen that if only gravity is doing the work, mechanical energy is conserved, and the final mechanical energy at the end will equal the initial mechanical energy at the beginning. However, if there are other forces doing work, this becomes the work energy principle, and we say that the final mechanical energy equals the initial mechanical energy plus any work done by non-gravitational forces. And you can think of this as like doing an energy audit. Check how much energy there is at the end of the problem, compare it with the energy at the beginning of the problem, and then take into account any extra work that has been done by the extra forces. So here we have a skier slides from rest down a slope 400 meters long at an angle of 30 degrees. What is her speed at the bottom of the slope? And the important thing here is that it is a smooth slope. So the only force that is doing work in this question at the moment is gravity. So if we take the bottom of this diagram as our zero potential energy, and if we look at A first, the kinetic energy at A when she set off was 0, and the potential energy was mass m times gravity g times the height, and we can get the height above our zero potential energy level by trigonometry as 400 sine 30. So the potential energy at the top of the hill is 200 mg joules. If we now look at B, the kinetic energy at B is a half m, and I'm going to call the speed v squared, The potential energy at B will be 0 because that's our 0 potential energy level. And we know, because it's a smooth slope, there's no other forces doing work, that final mechanical energy equals initial mechanical energy. So the final potential energy was 0. The final kinetic energy is a half mv squared. The initial potential energy we've just found was 200 mg, and the initial kinetic energy was 0. M cancels out, so the answer is independent of the mass of the skier, and we get the speed is 62.6 meters per second. As we can see the full method there. So that's an example of conservation of mechanical energy. At the bottom of the slope, the skier encounters rough level ground. There is a constant frictional force of 0.25 mg newtons, where m is the mass of the skier, and this frictional force opposes the motion of the skier across the ground. How far does the skier travel over this ground? So we know we've already found the speed as they reach ground level. We found it in the previous problem. We know v, and eventually the skier will stop. It's level ground, so we don't need to consider potential energy. So what do we know? We know the final kinetic energy of this level ground will be 0, and we already know from the previous part of the problem the initial kinetic energy just as they got to ground level was 200 mg joules. So we've already calculated that, and we need to start thinking about the work done by friction. Work done by friction must be negative because friction always does negative work, so it's minus the frictional force, which is 0.25 mg, times the distance covered d. Now when we look at our work energy principle, we've got final mechanical energy equals initial mechanical energy plus work done by the resistance. So final mechanical energy, there is no potential and there's no kinetic at the end. Initial mechanical energy, there's no potential but there is some kinetic. There was 200 mg of kinetic plus work done, and the only force that's doing work in this problem is the resistance, and the resistance is done minus 0.25 mgd joules of work, which gives me a distance of 800 meters. So be careful there, the work done by the resistance must be negative. Here we have a car on a circular warm wheels track. It's released from rest and it at a point A whose radius makes an angle of 50 degrees to the downward vertical. It passes through the downward vertical and rises to point B where it comes to rest again, and that is an angle of 40 degrees. So at B it will come instantaneously to rest. We've got to find the average resistance to motion experienced by the car. The mass of the car is 50 grams. So we need some assumptions here. So we're going to make some assumptions that the path is the arc of a circle. We can treat the particle, the car as a particle, a point in space, and we're going to assume that the initial and final speeds are 0, for example. So the first thing we need to do is to find the change in the potential energy. So here B is the final point, which is below it, and I've defined that as my zero potential energy level. So we found the distance CD by doing trigonometry as r cos 50, and CE is r cos 40, and therefore the gap between them, which is what I'm interested in, is r cos 40 minus r cos 50. So the initial potential energy at A we can work out using mg times dE is 0.060 times r. That's our initial potential energy. So by working the work energy principle now, this change in mechanical energy is going to be the work done by the resistance to motion. So we need to think about the work done by the resistance. The first thing we need to do is to find the length of the arc. So we need the distance travelled by this resistive force. So the length of the arc, noting this is a right angle, is r times pi by 2, and hence the work done by friction. Don't forget, friction always opposes motion. So the work done by the resistive force is negative F times R times pi over 2. So looking at the work energy principle, I'm going to do this now using final mechanical energy equals initial mechanical energy plus work done. So the final potential energy, that was my zero level at B. Final kinetic, it comes to rest, so there wasn't any. Initial potential, we've just worked out, is 0.060 times R. Initial kinetic at the beginning was 0 because it wasn't moving, plus work done. And the only force doing work was the resistive force F. And we've just found that the work done by F is minus F times R times pi by 2. The radius will cancel out, and this equation will give me the resistive force is 0.038 newtons. So we've seen the work energy principle in the form final mechanical equals initial mechanical plus work done. However, weight itself can be regarded as doing work, and the formula could be rearranged to give the work done by the external forces plus the work done by the weight is the change in kinetic energy. In other words, you can think as the work energy principle as total work done by all the forces equals change in kinetic energy. So we've got two approaches here. Final mechanical equals initial mechanical plus work done by the non-gravitational forces, or the total work done by all the forces is change in kinetic energy. So let's have a think about this skier. 660 kilograms, slides from rest down a rough slope 400 meters long at an angle of 30 degrees. We know the speed at the bottom is 40 meters per second, and we want to find the frictional force acting against the skier. So if we think about A first, so at A, let's think about the potential energy. I'm going to take zero potential energy again at the bottom of my diagram. So that's zero potential energy. So the potential energy at A is mg, and the height using trigonometry is 400 sine 30. So that gives me a potential energy of 60g times 200. The kinetic energy at A is 0 because the ski wasn't moving. If we look at B, the potential energy is 0 because that's my zero potential energy level, and the kinetic energy at B is a half times the mass times the speed squared, so that's 40 squared. And then the important bit, the work done by friction, and we know that friction will do negative work, so the work done by friction is a negative F times 400 And now if we do, I'm going to do final mechanical equals initial mechanical plus work done. So the final potential is 0. The final kinetic is a half times 60 times 40 squared. Is the initial potential, which was 200 times 60g, plus the initial kinetic, which was 0 because it wasn't moving, plus the work done. And the work done by the resistance was minus 400F. So the work done by the resistance is minus 400F. Notice that negative work. So the two approaches that you could use here, I've just demonstrated final mechanical energy equals initial mechanical energy plus work done. Or we could do total work done by all the forces equals change in kinetic energy. So here, in this method, here we've got the work done by gravity. Here we've got the work done by the resistance, and on this side we've got the change in kinetic energy. Both will give exactly the same answer for F. And that brings us to the end of work, energy and power 1.